Hello everyone, this is a presentation that summarizes a class project for EEE 475, Medical Image Reconstruction and Processing. We are a group of two, Mavinun Polatolo and Orhun Caner Eren. Most of this course is aimed at teaching MRI reconstruction algorithms for parallel imaging. But why parallel imaging? Because one of the main problems of MRI is the long acquisition time, and parallel imaging methods offer a solution by decreasing the amount of case-based data that is needed. In parallel imaging, the same data from multiple coils or channels are acquired and used together in reconstructing an image. However, now we have a lot of data. If a single slice were a 256 by 256 matrix that holds complex values, then in the third dimension extended 180 slices, and there were 8 coils, then we would have that amount of data points. So now we would like to use coil compression to decrease the amount of data to be processed. So there are many methods for parallel imaging such as SENSE, GRAPPA, and SPIRIT, which have been implemented in class assignments. SENSE reconstruction, being an image domain method, uses coil sensitivity maps to generate a single image. Whereas in the case-based methods, the non-acquired case-based points are filled using neighboring points. One component of the project was to estimate coil sensitivity maps using different algorithms. The other component was to apply coil compression and test the results on various reconstruction methods. There are two datasets that we used. The first is the 16-channel data of a physical phantom taken in a 3 Tesla scanner using a turbo spin echo sequence. The individual slices are stored in a 256 by 340 complex matrix. The second is an 8-channel data of a human knee taken in a 3 Tesla scanner. Individual slices are 320 by 320 complex matrices.
MRI signal of hydrogen atom varies according to the proximity to the receiver coil, shape of the receiver coil. This proximity and the other properties of this imaging system can be modeled as coil sensitivity. The knowledge of the coil sensitivity is one of the most fundamental components of sense reconstruction and coil compression. However, coil sensitivities are hardware dependent in nature, therefore it requires many measurements for an accurate assessment. Even though there are many measurements, there are too much unknowns to consider for correct measurement, such as placement of the patient, imaging position, distance to the coils, etc. There are many methods that have been developed for estimating coil sensitivities by acquiring a calibration data from the center of the case space. We have attempted to implement 3 such algorithms in our project before applying coil compression. First algorithm we implemented is the most common and the most basic algorithm that can be implemented for a coil sensitivity estimation. This method only needs a relatively small fully sampled calibration region. It uses fully sampled data to generate low-resolution image for each coil, and then generates an overall estimate image by sum of squares. Since coil sensitivity is modeled as a coefficient multiplying the ideal image, and the result is of this multiplication is the acquired low-resolution data. It can be calculated by dividing the acquired image to the ideal image, which is estimated as sum of squares image. The calibration size affects the map estimation. For example, for larger calibration size, the estimates becomes more biased. As seen in the comparison between left small calibration size and the right large calibration size, the details began to be observable such as tissues. However, coil sensitivities do not depend on the object being imaged therefore, too large calibration size makes estimation inaccurate. However, this does not mean that small calibration size is enough to achieve a good estimate. As seen in the left image, small kernel size does not contain enough information to successfully estimate the coil sensitivities. Therefore, it performs poorly on the sense reconstruction technique. If we need to require 64 by 64 calibration data and increase the scan time, why we didn't use SPIRIT or GRAPPA directly and then we get a better image quality? Therefore, we need a smaller way and smarter way so that we don't have to acquire this much data, but only acquire 1/16 of it as 16 by 16 data. This smart technique is called grappa, or spirit extension. In this technique, we only acquire 16 by 16 calibration data, and we use expensive and accurate algorithms to expand this data for coil sensitivity estimation. Later, this sensitivity estimation will be used for compression and dimension reduction. Therefore, it will take less reconstruction time compared to the full reconstruction. We are also acquiring 1/16 of the data we should acquire and using undersampled data that we should have collected anyway. Therefore, we still have less acquisition time. An example for this extension can be seen in these images. Even though the reconstructed image from the extended image is not good as the fully sampled 64 by 64 data, the improvement shows that extension is a nice method when fully developed for clinical usage.
The wavelet-based estimation is an iterative one, where a multi-resolution analysis, MRA, is done followed by a maximal value projection, MVP. The MRA step is basically a wavelet transform that decreases the spatial information of the coil images. This step is similar to a low-pass filter. The MVP step compares the original coil images and the output of the MRA pixel by pixel. If the original pixel has a larger value than the MRA output, then the MRA output is replaced by the original pixel image. This allows conservation of the high contrast edges. We couldn't implement this method to its fullest. However, we did wavelet thresholding to remove spatial content and MVP as suggested, which resulted in 16 coil estimations, which were then used in coil compression. In the image, we can see 9 of these eigencoils, and these resulted in a sense reconstruction that has aliasing artifacts. The aliasing artifacts can be seen on the top and the bottom, since Rx is equal to 2 and Ry is equal to 1. The performance gets worse as the acceleration increases. In the original publication, which can be found from reference number 2, there is also a metric called the inhomogeneity index that allows the code to decide which level of wavelet decomposition to choose as the output of the MRA step. However, due to time constraints, we were unable to implement this. Instead, we chose a constant level of 4 by looking at the intermediate transform results. And another aspect to be improved is to try another type of wavelet transform for the MRA operation.
Coil compression is an algorithm for decreasing the computation time by eliminating redundant data. Coil compression can be viewed as principal component analysis, PCA, which is a common tool in reducing the dimensions of the data. In coil compression problem, each pixel is a component of coil sensitivity, and each coil is a feature of this data. Applying PCA to this coil sensitivity map gives perpendicular components in a new basis set, which is linear combination of the original dataset. And projections on this new basis gives a new points which is initially in the same dimension as the original set. However, good part of applying PCA is that now the data is organized in new basis set of which the importance and the energy information contained is in known. By applying a threshold to the energies, low energy components can be discarded with a minimal loss in information. Also, since the measured data contains noise, small energy components can be assumed as noise, and by eliminating such low energies can boost SNR of overall image as well. After transforming coefficients, same coefficients can be applied to image and Fourier domain as well. Reason for this is that this operation can be viewed as a linear operation and is not affected from Fourier transform. Therefore, it can be applied by either domain. This information is used to generate k-space data for each eigencoil without applying additional Fourier transform. Intensities in the eigenimages related to the energy contained in them. As seen in each image, the intensity drops, suggesting the energy drops as well. There is a positive and a negative aspect of this energy drop. The positive aspect is that this drop in energy is so significant that in the first 4 coils, 98% of the energy is gathered. This shows that only half of the coils are adding different data to the system, and almost half of the data is redundant. When only 4 coils are used for reconstruction, there is a significant improvement in the noise level of the Grappers reconstruction as seen in the images.
We tried to incorporate coil sensitivity estimation in our previous work that we have done throughout the course and explore the effects of coil compression. We conclude that better sensitivity estimations lead to better compression and faster reconstructions. Also, we verified that by calculating eigencoils, we can eliminate some noise and calculate the upper limit on the acceleration factor in data acquisition. Thank you for watching this video.